Hello, I am Sean Maloney, and today I'm going to present my research on a few important transforms used in digital audio signal processing. Before getting started, I was interested in researching this topic after learning about Fourier analysis in class. As an audio engineering major and computer science minor, I enjoy creating and learning about audio software and digital audio technologies. I wanted to learn more about how Fourier analysis is used in relation to digital audio, and that is when I stumbled upon various transforms such as the Fourier transform, the discrete Fourier transform, fast Fourier transform, and the modified discrete cosine transform. This may be a good time to explain what a transform is as well. At its core, a transform is a mathematical equation that converts the input from one domain to another. In the case of the Fourier transform, this transform is able to convert its input elements from the time domain to the frequency domain, as we will learn about shortly. These transforms are utilized in many ways when it comes to audio, from creating a simple spectrogram to converting files to different formats, even to creating voice recognition software. To start off, we must recall a few concepts previously learned in class. You may recall the idea of superposition, which states that the sum of any number of waves is also a wave. From this idea, we can derive a few additional concepts: Fourier synthesis and Fourier analysis, named after the French physicist Joseph Fourier. Fourier synthesis is the creation of a complex wave from multiple sine waves. Fourier analysis is the examination of a complex wave by finding the simple waves that it is composed of. The process of doing so is commonly done by utilizing a mathematical tool called the Fourier transform. In the upper right-hand corner, we see a relatively daunting formula. This is the Fourier transform. Without delving into the nitty-gritty math of the function itself, we will note a couple things. First, it assumes an infinite set of values to be inputted into the equation, as we see the integral starts at negative infinity and continues to infinity. Because of this feature, the formula is not very applicable to digital audio. That is where the discrete Fourier transform comes in. The discrete Fourier transform is basically the Fourier transform, except it deals with a finite number of values. If you look at the Greek letter sigma in the discrete Fourier transform, we see that it is the sum of values starting at n equals 0 to the total length of samples, which is noted as big N minus 1. In the most basic sense, if we take an input sample of audio data with a given length, the output of this equation will be the simple sine and cosine waves that make up the complex waveform. In doing so, we are transforming the input from the time domain to the frequency domain. This is why this equation is referred to as a transform. If you take a look at the modified equation circled in blue, you see that the second half has been swapped out with two components, a sine and cosine function. This is done thanks to a guy named Euler, who proved that the second half of the top equation is equal to the sum of sine and cosine functions. For a better understanding, let's take a quick look at an example. Here's a small example of how data is transformed using the discrete Fourier transform. First, take a look at the sample set size. We have 4 total samples, so the size of the sample set is 4. This is also referred to as the window or frame size. To make more sense of what these samples actually are, imagine an analog to digital audio converter samples a signal at a certain frequency, and these 4 samples, x0, x1, 2, and 3, are the first 4 points that it sampled, so their values represent their voltage/intensity at that specific moment in time. We see that 3 of them involve the letter I, which denotes a complex number. Complex numbers in the Fourier transform indicate how much of the energy for a given frequency is in the sine or cosine part. So, in a basic sense, this helps indicate the phase. If you enter each sample into the formula, the output is a set of imaginary numbers which represent the amplitude of different frequencies. Therefore, we see that we are able to convert the input from the time domain to the frequency domain. Since we moved from the time domain to the frequency domain, the most obvious application for the discrete Fourier transform is with spectral analysis. Being able to take an audio file and see what frequencies it is made up of allows us audio engineers to do cool things like take out unwanted noise or create a spectrogram. Other uses include perceptual audio coding, such as converting audio into MP3, as well as, in a more simple case, finding a radio station. While the discrete Fourier transform is cool and all, a major drawback is that when implemented into computer programs, it's not very efficient at all. When evaluating the runtime of the DFT, it has a time complexity of n squared in big O notation. This means that if the sample size is 1,000, it'll take 1,000 squared operations to complete the equation. This is really slow and not ideal for audio processing in real time. Thankfully, there is a more efficient version of the DFT, conveniently called the fast Fourier transform. The fast Fourier transform was introduced by J.W. Cooley and John Tukey in 1965. The algorithm they came up with basically breaks down the sample into more manageable parts, and then the discrete Fourier transform is recursively run on these smaller sample sets. While other people came up with later versions of the FFT, this one is the most popular and widely used today. When looking at the time complexity for the FFT, it reduces the computation time from n squared with the discrete Fourier transform to n log n, which is a lot faster. Looking at the chart to the right, we see that with a sample size of 8,192, the FFT takes only 2.6 seconds to complete, whereas the DFT takes 12.6 seconds. While the FFT is great, there are a few drawbacks. The first is that depending on the implementation, the FFT can actually be less accurate than the DFT. Looking at the error analysis of the FFT and DFT, we can clearly see that the DFT tends to have less margin of error in its output than the FFT. It is important to note that the FFT is still much more popular to use than the DFT in digital audio. And as stated previously, smart implementations of the FFT should not have much error at all. Another drawback of the fast Fourier transform is that the frame size is most often restricted to 2 to the n inputs. This once again depends on the characteristic of the algorithm being implemented, but most often this restriction appears. Therefore, window sizes must follow the pattern of 512, 1024, 2048, and so forth. And this is where we run into an issue. Due to the nature of the fast Fourier transform equation, the input signal is assumed to be periodic. This basically means that the start and end points of a sampling frame are interpreted as if they are connected together. If you have a periodic wave whose period starts and ends at an amplitude of 0 within a frame, then there's no issue. However, real-world input signals are almost never simple sine waves that magically line up to the size of the given frame. For example, if you want to see the spectrogram for a song that you're mixing, there will likely be artifacts that occur from the output of the FFT, since the input data is incredibly unlikely to have a period matching the frame size. The image at the right helps to visualize this. In simple terms, if you repeat the signal in figure A, it'll sound normal because it has an integer number of periods in each window. If you repeat the signal in figure B, it'll sound abnormal because a period does not start and end at the window boundaries. Thankfully, there is a solution to this problem as well. This solution is the idea of windowing. Windowing is a process of applying a function to the input data before the FFT is taken of that data. The windowing function basically makes sure that the window within the frame starts and ends at 0 by adjusting the shape of the overall waveform. Looking at figure A, we see that when the measured signal is periodic and an integer number of periods fill the acquisition time interval, we get a very clean output from the FFT. In figure B, we see that when the number of periods in the window is not an integer, the endpoints are discontinuous. These artificial discontinuities show up in the FFT as high-frequency components not present in the original signal. This is also known as spectral leakage. In figure C, a window function is applied to the signal, and then the FFT is performed on that frame. Windowing reduces the amplitude of discontinuities at the boundaries of each finite sequence. This makes the endpoints of the waveform meet and therefore results in a continuous waveform without sharp transitions. While the output of the FFT is not as clean as figure A, it reduces the amount of unwanted information a decent amount when compared to figure B. Now that we are aware of the FFT, an incredibly interesting use case for this transform is with speech recognition systems. As discussed previously, if we take a signal in the time domain and convert it into the frequency domain using the FFT, we can plot the data and get a spectrogram. Going a step further from here, we can then train a deep learning model and build a speech recognition system. As we see in the image below, each spoken word has a unique image when recorded and plotted on a spectrogram. Just like how we use letters to spell and read words, we can train a deep learning model to recognize patterns in a spectrogram and relate them to words. One last transform to note is the modified discrete cosine transform, or the MDCT for short. This transform is different from the DFT and FFT as it deals only with cosine waves rather than a combination of sine and cosine waves. The interesting aspect of the MDCT is that it outputs half as many values as it takes in. This means that it is very useful for lossy audio compression, like when you want to convert a file to an MP3 or MPEG. Just like the FFT, a drawback is that windowing is needed for a smooth sounding output for the MDCT. MP3 encoding can be defined in 4 steps, where the MDCT comes in the end of step 2. First, the sample is divided into small sets or frames. Then the FFT is applied to the sample with window sizes of 1024 samples. After this, inaudible data is thrown out. Then the MDCT is applied, which cuts the total size in half. After this, there are a few extra steps such as noise allocation and encoding. But we can see that the application of the MDCT is a crucial component to MP3 compression, as the point of compression is to reduce the size of the file without noticeable losses in quality. Similar to the FFT, there are a couple issues to note with the MDCT. First off, the size of the frame may not be ideal for the input audio data. Longer frame sizes work well with longer sounds such as wind instruments, but transient sounds like drums tend to sound distorted. If you decrease the frame length, however, the spectral resolution decreases. This is because if a certain input frequency is unable to complete a full period within one window, then this frequency cannot be accurately represented. A solution to this problem is the idea of adaptive window switching, where the window shape and frame length change based on the sample that is inputted. This would require some additional computing, but the result would be a better output. Let's have a listen to an example of why window shape and frame size matters with this video clip.
But now we come to the castanets, which are very strong temporal structure. And if you use the long blocks here, I don't know if you can hear it in this environment, but there's always a kind of in the front of each of the clicks of the castanets. You can improve it again by using the short or also the adaptive window. Maybe I just play the last example. So the clicks are sharper again when you do this.
In conclusion, we have gotten to learn about and compare 3 important transforms used in digital audio signal processing. First, the discrete Fourier transform, or DFT, is the digital version of the Fourier transform. It uses both real and imaginary numbers to represent the signal. The modified discrete cosine transform, or MDCT, differs in that it only uses real numbers. The fast Fourier transform, or FFT, is just a faster way of calculating the DFT, and is great for general purposes, but takes up more space. Lastly, the MDCT uses half the amount of data as the DFT, which is why it is used when data size is important, such as with creating MP3s. Ultimately, these mathematical equations can be utilized to do incredible things in audio, from having different ways of analyzing spectral content to contributing to speech recognition systems. I hope you found this topic as interesting as I did. Here are my references, and thanks for watching.